Hello, the paper we are reviewing today is DiffuScene, subtitled Denoising Diffusion Models for Generative Endorsing Synthesis. This paper comes down to one sentence. The previous state-of-the-art ATISS placed the furniture one at a time in order. DiffuScene denoises the whole room at once. We'll look at why that sentence matters, how it is implemented, and where the paper's claims differ from its own results. Let's start with the problem and where prior work got stuck. 3D endorsing synthesis means generating a whole furniture arrangement for an empty room. What objects were facing which way at what size? It's harder for one reason. Objects are not independent. A nightstand on the left implies another on the right, so the model must learn a joint distribution, and the object count varies per room. Of the paper's use cases, the one that matters is the data engine. Training 3D scene understanding models needs large-scale labeled data that can't be built by hand. That's why diversity matters here. Now the table rule-based methods require handwriting. Every nightstand goes beside the bed need a slow optimization path, and any arrangement not covered by the rules is never generated. GS are fast and sharp, but prone to mod collapse. Thousand bedrooms become variations of one, better from the data engine. VAEs are the opposite. Broad coverage, low fidelity. Sync to gen patched that with Bayesian optimization post-processing. So it brings back the very optimization stage rule-based methods used. So diffusion is a natural result. GN's fidelity and VAE's coverage at once, already demonstrated in 2D. That leaves one question. What tensor do we turn a scene into? And the bottom row, diffuse scenes, real comparison target is ATISS. The other three were already far behind. So let's look at why ATISS is the problem. The top row is ATISS better than nightstand than wardrobe than lamp. This tab only sees what has already been placed. Critically, when you place the fourth, there is no way to revise the first. The bottom row is diffusing. Every object is just simultaneously, and at every denoising step they see each other. Two problems. First, every accumulation. If the bed ends up badly placed, every subsequent object is decided on that premise with no way to correct it. Second, and more fundamental, the ordering isn't it in the data. The bed comes before the nightstand. There's no meaning in our room. Yet, autoregressive models impose an arbitrary ordering and factorize the conditional along it. The purpose of words, rather than representing a scene as an ordered object sequence and diffusing them sequentially. Although this diffusion simplifies and eases the approximation of the joint distribution. Another that doesn't exist is imposed, and the model capacity is spent in learning it. That's this diffusing framing of the problem. So how does DiffuScene answer that, and what does it claim to contribute? Quoting related work, we approach scene generation as an unordered object set diffusion process where we explicitly model the joint distribution of object compositions. Multiple object properties are denoised synchronously, enhancing inter-object relationships and object composition plausibility. The three contributions are on screen. The first applies diffusion to scene generation. The second is design with it. The third follows. The second is the substantive one. In the evaluation later, that element alone lifts the symmetry metric from 0.5 to 0.72. Legonette is concurrent work, also diffusion-based, but three things differ. It predicts one to the location and orientation, takes a floor plan as input, uses Lang Langevin dynamic score matching, and its denoiser is the transformer. Division generates semantics and geometry from pure noise, uses DDPM and UNet 1E with attention. Convention is scene-graph conditioned, and the diffusing does not support scene-graph conditioning. It appears only from comparison. Now the method. Let's unpack what a single object becomes as a vector. I is a 3D location, origin at the floor center. S is 3D size. C is the class. F is 32D shape code. Why not use the rotation angle theta directly? Why decompose it into cosine and sine? Because angles are circular. 359 degree and 1 degree are 2 degree apart in reality, but 358 apart numerically. Near 0 degree, tiny Gaussian perturbation pushes the value toward 360. A huge error to the model, though the geometry barely moved. Mapping to a point on the unit circle removes the discontinuity, not a choice, but mandatory pre-processing for continuous diffusion. Next, object count varies per loom, but diffusion demands a fixed size tensor. The fixed and empty class fills unused slots, padded to n. Note there is no occupancy head. If class diffusion outputs empty, the slot is unoccupied. Count prediction is entirely absorbed into class prediction. Bedrooms have n equals 13 and 22 classes, so dimension is 62. Dining and living rooms are 65, except the paper never staged D numerically. Those figures are computed from the n and the class counts scattered in Appendix B, a reproducibility defect. So one bedroom is a 13 by 62 tensor, remarkably small. This is the basis for the paper's claim that its representation is more compact than boxers or neural fields, and therefore suited to diffusion. Let's look at what the shapecode F, half the vector, is used for. The easiest thing to misread in the paper. F is a 32-day latent from a 2048 point cloud through a folding net style GAE. Hard comparison from um, 512 the global latent down to 32. First, appendix 2, they normalize before diffuse. While we apply KL regularization, the value range of latent cause is still unbound. To make it easier to diffuse, we scale the latent cause to -1 to 1, and rescale at inference. The DPS noise schedule assumes data roughly in -1 to 1. If a shape code ranged from -50 to 80, noise with a beta of 0.02 would do essentially no damage. Without it, training doesn't work. And Appendix 3, for each instance, we perform the nearest neighbor search in the 3D future dataset to find the CAD model with the same class level and closest geometry feature. So I've never produced a mesh. It's a query key into a 32D catalog, and every piece of furniture in generated scene already existed in 3D future. So what does diffusing F5? Evaluation C4 answers without F, retrieval select same class closest bounding box size. Exactly what ATISS does with F diffused jointly. The model learns at the code level that two nightstands must be the same model, emitting the same shape code, not something of a similar size. Symmetric pairs go from 0.5 to 0.72. That is this paper's core contribution. Now that the scene is a tensor, the diffusion process, equation 1 is just the definition. The whole forward trajectory is a product of a single step transition. Equation 2 is one step, shrink the current value or by root 1 minus beta t and add noise of various beta t. The shrink is there because adding noise without it makes the variance blow up. That's the variance preserving scheme. Equation 3 is the key trick. No iteration. You jump from x0 to xt in one shot. Alpha bar t is the cumulative product of the alphas. The ratio of how much original is left. At t equals 0, it's 1, the original intact. At 2 equals 1000 near 0, pure noise. So training can sample a random t and construct that point directly rather than run 1,000 steps. The beta schedule is linear from 0.0001 to 0.02. T equals 1000. The GPM's default verbatim. Verbatim? Be precise about erasing here. X is 13 by 62 numeric metric. Rotation size rotation. Allocation size rotation. The class what hat and the shape code all get the same Gaussian noise. Noise added to a 0010 vector, representing a bed. The paper offers no justification for the treatment. We've added the noise. Now we reversed it. Equation 5 shows each reverse step is Gaussian. The variance is not learned. Sigma t is fixed by formula. The paper mentions learnable covariance and doesn't use it, and the citation there is wrong. Learnable covariance is nickel and Darial is improved DDPM and DDIM. One notational warning. The network parameters are pi, not theta. Theta is already taken by the rotational angle. The easiest thing to trigger on when reading this paper. Equation 6 is the method's most important equation. Epsilon prediction. Rather than predicting mu directly, the model predicts the noise that was not added. Given epsilon, you subtract it from xt, although the scaling and mu is computed. The only learned object is epsilon pi. Here's why it's better. What was the original room behind this noise when, at t equal 900, could be almost any room? Uh, mm, mm, but what noise was added is always a standardized draw from N, O to I. The target has the same scale at every T, so training is far more stable. The loss, three lines of variational bound derivation collapse to the MSE between the added noise and the predicted noise. The paper skips that derivation and defers to DDPM fair since it's the identical derivation. The paper adds one more loss here. This is its second contribution. X0 tilde T is the current estimate of the cleansing, recovered from the epsilon prediction in one step via equation 6. IOU can't be measured for one noise xt, so you estimate the clean room first and measure overlap there, a sensible workaround. Then sum the IOU over every pair of boxes. A bed intersect a wardrobe gets penalized. The weight is fixed to 0.1. Note the paper never writes the combined loss of LSCE and LIOU. This 0.1 is the only weighting information given. The interesting part is alpha bar t. Alpha bar t goes to zero as t grows, which means the IOU penalty is effectively switched off in the high noise regime. The x0 tilde at t equals 900 is not trustworthy, but computed from what is essentially noise. Penalizing IOU there would make training unstable. Near t equals 0, alpha t approaches 1 and the penalty applies in full. So the geometric constraint operates operates only at the low noise end. The global layout is decided by the diffusion process and the IOU only fine-tunes at the finish. The paper never states this design intent. It puts alpha T in the equation and moves on, a well-designed detail. With both rushes defined, let's look at the network that predicts epsilon. As t comes to n by d, the objective axis becomes the sequence axis and d becomes the channel axis. That makes the 1D convolution unusable. Separate encoding has a per attribute be box close to zero. Then one conversion and the self-content attention alternate with scale conditions. A new unit transposed into 1D. The prediction has split three ways again. Loss computed separately. Self-attention is the heart of it. Appendix D. The self-attention layers effectively aggregate all object features and explore inter-object relationships, facilitating the learning of a global context. This is how a bed sees the nightstand and one nightstand sees the other. That's where symmetry gets made. Why 3 has three, 32 of the 62 dimensions or the shape code, more than half. Through a single head, the shape code dominates the MSE loss and the 3D location is drawn out. Training runs on single RTX 3090 with batch 128 against 2D diffusion burning dozens of A100s for rigs that are low compute cost. The payoff of a 13 by 62 tensor, but some things aren't in the paper. Layer count, channel width, head count, the optimizer, none given, and not a single sentence on how times t is injected. Time embeddings, sinusoidal encoding, film, adagian, no mention. The diffusion model T injection is required and it's missing. Let's see what the trained model can do. This is the cleanest piece of the paper's design. On the left, scene completion. M object Y are given. In the paper's words, we keep the already known elements and only hallucinate the missing ones through learnable reversed Gaussian transitions. So you freeze M rows and denoise the remaining and minus M. Is in painting applies to the object axis. On the right, the arrangement diffused as a U location and orientation, 5 dimensions. Frozen as the condition is V sizes class shape. The furniture stays and you decide only where and how it sits. Completion is row-wise masking. The arrangement is column-wise masking. Same tensor cut horizontally or vertically. Neither requires any additional training. Take the unconditionally trained model. Apply a different mask at inference and that's it. And an AR model cannot do this structurally. Its order is fixed, so you can't resample a middle item to move the third piece of furniture. Everything after it depends on it, so you regenerate the slot. This is the capability built by giving up ordering, the freedom to condition on an arbitrary subset. The third contribution isn't a separate claim but a property that follows from the design. That was the mechanism. The paper's first page shows the result. The complete panel on the left. The top is the input picture scene, a sofa, a channel, a chair, a low table. And the output below, the input objects are preserved, while dining table, chairs, and the lighting are added. That is raw white masking doing its work. The rearrange panel on the right, objects are scattered in the input and arranged along the walls in the output. That is the column-wise side. The paper labels this scene compilation from partial scenes, and the scene arrangements of given objects. The original figure 1 has one more panel, generating a scene from a text prompt that isn't a condition you can impose by masking. That's where we go next. There is one condition masking can't express text. A sentence like "there is a bed." Two nightstands are next to the bed goes into frozen board, producing 48 by 768 embedding injected into the denoiser via cross-attention. Query is subject key and the value are words. Notice both not clear. Look at how the prompts were built. Randomly pick 3 objects, count per category for the first in sentence to find pairs at distance under 1.5, attach a relation word. Sample 0 to 2 relation sentence. These aren't human written sentence. Their template. The something like a cozy Scandinavian bedroom doesn't exist in the training distribution. The biggest limitation in the method section is the absence of classifier-free Gaussians. CFG has been the de facto standard for conditional diffusion since 2022. 2022 stable diffusion 32 image and all used. It's the knob for how strongly the model follows the condition, and it isn't applied here. Gaussian scale is never even defined, and Ho and Saliman's CFG papers teaching the bibliography, but is never used in the body. Sampling is plain ancestral sampling. For reference, this paper's text matching score is in the user study is 55%. It's a two-way choice. So chance is 40%. The message is done. Now the experiment starting with the setup. The data is 3D prompt with CAD models from 3D Future. After filtering, 4 1,041 bedrooms, 900 dining rooms, 813 living rooms, spread 80 and 20. Every filter follows ATISS, securing fairness of comparison. On the very baseline, the original ATISS conditions on a 2D room mask the floor plan. Diffusing generates from pure noise, so the authors trained it on unconditional ATISS without the mask. The right call. A conditioned model against an unconditioned one would not have been fair. The metrics FID and KID are measured on 256 by 256 top-down orthographic semantic maps. A view from above with each object painted is classed color. SCA is the confusing one. Is the accuracy of classifying real versus generated and closer to 50% is better, and 50% is the classifier is completely confused. OBJ, symmetric, and PIOU are likewise better the closer they are to Jetty. The Jetty is ground truth, and particularly symmetric is the number of symmetric pairs. We'll be watching that one throughout. There's no out-of-bound metric. Nothing measures whether furniture penetrates a wall. PIOU is the only measure of physical plausibility, and it captures only furniture or overlapping furniture. In practice, going through a wall is the more damaging failure, and it isn't measured. So the main result is with all 12 cells, every room type, every metric, but the spread across matrix is large. FID barely improves. ATISS 18.6 versus diffusing 17.21 on bedrooms, a 7% again. On the number alone, it's hard to argue diffusion's effect is large. KID 1.72 to 0.7 on bedrooms and 5.62 to 0.72 on dining rooms. 7.8 for the reduction. A different order of improvement from FID. The next shade, 61.71 to 52.15, given that 50 is the ideal. The classifier identifies ATISS is output at 62% accuracy, but against diffusing it drops to 52% chance level. Why do FID and KID differ so much? FID has a less sample size bias. FID Placed on small samples, measured on 1,000 samples, KID is the more trustworthy of the two here. Reporting it alongside was a good choice. In the user study on test-conditioned synthesis against ATISS, diffusing was preferred 62% on realism and 55% on test matching. Over 225 scenes with 45 users, but it's two-way, so 50% is chance and no confidence intervals for significance tests are approached. Next, sentence statistics. This is the most notable result in the paper. The bedroom row OBJ 4.99 against GT's 5.0. Symmetry is 0.72 against 0.71, PIU 0.43 against 0.43. Matching to the second decimal, hard to call coincidence. Strong evidence the distribution was learned faithfully. ATISS sim is 0.33 against GT's 0.71, not even half. This is a autoregressive weakness on symmetry numerically. Placing on nightstand ISS cannot express the plan. Place another opposite later. Divisions not two nightstands see each other at every step. The structural difference is what 0.33 versus 0.72 measures, but the underlying cell dynamo PIU sync to gens 0.55 is closer to GT than divisions 0.665 since GT is 0.48. The paper bulge that cell itself. The authors know, and yet the body says, or our method consistently performs other methods on all metrics. For table 1 that holds, for table 2 it doesn't. The table marks to lose. The prose doesn't reflect it. Let's see which component the performance actually came from. Bedrooms only. C5 first. The row verifying the paper score contribution. Remove shape code diffusion and sim correct from 0.672 to 0.5 against GT of 0.71, while the other metrics barely shift. Equality only rises from 17 to dot 21 to 18.4. Only symmetry breaks badly. The second claim verified a well-designed evaluation. C1 is more interesting. Swap the denoiser for a transformer and apply the explode from 17.1 to 229. that 08 SCA jumped from 52 to 74 by a wide margin, the largest degradation in the entire appellation. And yet Appendix D describes that degradation as marginal, or 70% worse. FID is hard to call marginal. Every other oblation moves by 1 or 2 points. This one opens a 12-point gap. The author's probe doesn't match the numbers in their own table. As you will see shortly, this number also conflicts with the paper's central claim. To things absent from the table, there is no legend for C1 through C5. The descriptions on the screen are reconstructed by tracing back through the prose, and there is no elation on the number of diffusion steps. Whether T needs to be 1000 or 100 would do is never verified. The aberration moved seemed um, from 0.5 to 0.72. The paper also shows the number as a picture. There are two comparison pairs and in both. A is without shape diffusion and B is with it. In the left pair, the nightstands flanking the bed have different shapes. In A, one is an open shelf, the other a drawer unit. In B, the same shape appears as a pair. The right pair is the same story. A has a nightstand on one side only. B has matching nightstands on both. The reason the paper gives is a single clause. Due to the geometric awareness of the diffusion process and the shape retrieval, there is nothing further in the body or the appendix. To this are worth noting. Two pairs are shown, and symmetry is defined in section 4.1 only as the average number of symmetry object pairs in each scene. What counts as symmetry is never specified. Reproducing 0.72 independently would be difficult. That's the paper's content. Now the assessment, starting with what it gets right. First, the problem is defined precisely. A single shift or scene is an unordered set, makes error accumulation and other dependence disappear structurally, not a workaround. The problem setting was reformulated. Second, three applications from a change of mask, zero additional training, more generic and versatile isn't a separate claim. It follows from the design. Third, the contribution is narrow but clear. Diffuse the shade related to is a single idea, and the evaluation C4 verifies its effect precisely. Verifying without inflating is the right conduct. First, the metric choice is APT. On FID alone, this would have been a 7% improvement paper. The symmetry turned a can't form symmetry from a qualitative observation into quantitative evidence ATISS 0.33 A against GT 0.71. That contrast is the paper's central support. Fifth, reproducible scale. One RTX 3090 13 by 62 tensor, a rare descent generative model paper an individual researcher can reproduce. The four limitations the author's analogy in section 4.4 retrieved CAD models may not match the desired style. Textures come straight from the dataset, only single looms, and the dependence on 3 levels of fair list, but every item is framed as data and scope. The limitations of the method itself go unmentioned. Now the limitations starting with the craft of the paper itself. First, table forced caption and row libels disagree. The caption says bedrooms and living rooms, while the rows read bedrooms and living room. One is wrong. Second, more serious. The ATISS baseline numbers are identical across the table. Table 4's living room ATISS is symmetry 1.42, PIOU 1.73, table 6 dining room ATISS is also 1.42, 1.73. Table for bedroom 0.01 and 0.84 match table 6.2. These are different tasks, rearrangement versus completion, yet our four values coincide. The paper doesn't explore in explaining. With the first point, at least one table carries a wrong number or a wrong label. Third, the consistently outperforms on all metrics. Claim already doesn't hold. Fourth, the information needed to reproduce is missing. The value of the optimizer, the time step injection mechanism, not one sentence, one time embeddings, layer and channel counts the C1 and the C5 legend, none of it. Fifth, notation errors. Equation 3 is product index mismatch in the body, which is yet not intractable to optimize directly. Not plus intractable is a double negative. So you list as direct optimization is tractable, but introducing variational bounds. Next is what you do when direct optimization is interactively. The sentence contradicts the argument that follows it, plus the learnable covariance miscredit to DDIM, and the sentence fragment in the conclusion, all of it present in the published version. Now the limitations of the methodology itself. First and most important, unordered set is asserted, never argued, and the backbone structure conflicts with it. Search the full text. Permutation appears exactly once. Describing ATISS as permutation invariant transformer, the paper never discusses the permutation equivariance of its own method. Attention is permutation equivalent, but one convolution along the object axis is not. The moment a convolution kernel processes adjacent set elements together, an ordering is introduced. Object 1 and 2 fall in the same kernel. 1 and 7 don't. At that point, it is no longer a permutation invariant set. Second, the paper's own abelian research alongside that claim. The permutation equivalent pure transformers 1 degrades to FID 29.08, the largest drop in the elaboration, while C5 is a conversion backbone where equivariance does not hold. It's best as 17.21. The paper never relates its central water removal claim to the fact that its own permutation equivalent structure performed worst. Third, inference cost is never reported. A 1000 step DDPM versus ATISS at almost 21-fold passes. It's the comparison of leader most needed and not a single number is given. Learn time inference time speed. Nothing new. Meanwhile, related work called classical optimization computationally inefficient. First, Gaussian noise is applied to discrete variables. The class 1 hat is a categorical variable treated as continuous. Discrete diffusion such as D3PM and analog bits existed as prior work, yet there is no comparison and no discussion. Papers, no CFG, no statement of how the IOU of rotated 3D boxes was made differentiable, and no room mask support. Dropping the mask for a fair comparison is defensible, but a pro plan is normally available in practice. Having seen the limitations, here are directions that could address them. First, swap in a DDIM sampler. The cheapest improvement attach it to the trained DDPM with no retraining. Cut 1000 steps to 50. Plot the quality degradation curve, and the number of the paper omitted fields is serpent on 13 by 62 tensor. This makes the real-time interactive interior design tool feasible. Second, settle the permutation claim is experimentally replace conversion with a permutation equivalent operator and measure how much the output changes when the input order is shuffled. The separate Y-C1 lost equivalence or combos inductive bias. Third, hybrid diffusion, Gaussian for the continuous variables. Categorical diffusion like the 3 p.m. for the class alone. The heads are already split 3 ways, so almost no structural change is needed. First, bring the room mask back as a condition. Inject the floor mask via cross-rotation and add the outbound metric the paper lacks. Then you can measure and suppress wall penetration, the most damaging practical failure. Fifth, replace retrieval with generation. While the 32D latent into a 3D shape diffusion decoder and style mismatch and texture dependence, the authors admit deserve together. But there's a catch. 32 dimensions are too few for a mesh, and widening the bottleneck grows the dimensionality the scene diffusion must handle. The slide 6 trade-off returns. That is the real research problem. To close, let me summarize. First, represent a room as an n by d tensor and the rest is DDP, unchanged. Half the master answers had how do we represent a scene as a tensor? Cosine, sine, notation, empty padding, minus one-to-one normalization. Individually simple, but drop any one and training doesn't work. Second, the core contribution is shape latent diffusion, verified precisely by ablation C4, symmetry 0.372 against 0.5. The framework itself follows DPM. There's not a follow. A narrow contribution thoroughly verified beats broad one poorly verified. Third, 3 applications from a change of mask with no extra training. The capability bowed by giving up ordering on that AI cannot structurally support. First, but the central claim of unordered set competes with the UNet 1D backbone, and the permutation equivalent transformer degrades badly. The paper's claim and its actual performance driver differ, and it never discusses this, its biggest limitation. Fifth, the cost is 1,000 step sampling is never reported. No speed comparison against ATISS exists in the paper. The first gap follow-up work should close, and the exist with DDIM alone, and the lineage former started AR. ATISS matured algorithm attached diffusion to the pulse and diffusing diffuses are all attributes at once. Next, a discrete continuous hybrid, a fast sampler multiroom sense.